So now that we have found the relationship between the Sherwood, Schmidt, and Reynolds number through dimensional analysis in part 1, we are going to move on to creating simulated data, experimental data in Python, and then fitting that data to that equation we found in part 1 in 2 different ways. We're going to try the linear regression through matrix manipulation way in order to establish the coefficients A, B, and C, and then we're also going to use the sum of least squares method to try and find those coefficients A, B, and C. Like again, I said we're going to be generating artificial experimental data that could be that is different from what the textbook used to find their relationship. So the numbers A, B, and C from the textbook will be different, but hopefully they'll be similar to the coefficients that we find through matrix manipulation and sum of least squares method. So I'm going to start first with the linear regression method through matrix manipulation, and we always start with importing what kind of packages we need, and for this one we're just going to start with the normal one, import num_p as np. That's really the only function. We only need the numerical Python catalog for this one. We don't need any other functions to start out with, and so we need to define our variables first in terms of like what numbers we want for our experimental data. So we want, we're going into the NP catalog for the Reynolds number, and we want we want np.random because we want random numbers, and then we want it uniform distribution so that every number within the random number calculated has equal chance of being drawn or uniform. There's no bell curve, it's a uniform distribution. So the low in this case would be 2000, and this is from our book. The experimental equation in our book found that the relationship that I'll type out a little bit in like 2 lines is only valid from values of Reynolds number values from 2000 to 35,000. So as you can see, the uniform function needs a low, it needs a high, and then it needs how many samples we want drawn. So we want it from 2000 to 35,000 because that's when this equation is valid, or this relationship is valid with these specific coefficients. And then we want 100 numbers drawn. And we're going to do the same thing for the Schmidt number. It needs to be np.random, and again a uniform distribution so that each number is equal likely of being drawn. And again, this is from the textbook. This relationship only works for Schmidt numbers, from 0.6 to 2.5. And again, we want to pull 100 data points, or size is equal to 100. And now we will type out the equation I've been mentioning. This specific relationship is from our textbook, and it says that from these ranges for Reynolds and Schmidt numbers, A, B, and C are this. So A would be 0.03, and then we multiply that by the Reynolds number, and then we need 2 asterisks for raising it to a power, and then B would be 0.83, and then once again times Schmidt to the 0.44, so C would be 0.44. So now we know that is our relation that we're working off of. If we did numbers, from here, we would get the same exact coefficients for A, B, and C. So we want to generate a little experimental error or wiggle room so that we don't end up with the same exact A, B, and C coefficients. So we're going to be using the random normal function within the NP catalog to create this experimental error. So we want to do random np.random.normal, and then this function wants 3 things. It wants a LOC, which is like the mean. So we want the mean to stay centered around or located around the Sherwood number, so that stays as SH, excuse me. And then it wants a scale. So the scale would be our standard deviation. So let's say in this case we want to create a 10% error. We would just simply take our Sherwood number and multiply it by 0.1, not 2, 0.1 to create a 10% error in our data. So we're theoretically changing the Sherwood number by 10% to get fake experimental data that's still realistic. So now that that level looks good, I'm going to now hop on to a separate piece of paper and show you how linear regression works in terms of matrix manipulations, and then we'll type out the final equation that we get in Python and solve for our unknown matrix. So now we're moving on to the linear regression method through matrix manipulations, and we're going to start with just a simple example of y equals mx plus b. You would start by creating a matrix, and then you would have x1, x2, and then I went down to x5 in this case. So you would have different x values, right? So x1 through x5, and then you would create a column of ones next to that because you have I call this X, matrix X times matrix B, which is our unknown matrix. So when you multiply these matrices out, you get, let's say, do the first one, you would get X1 times M plus B, so B would be times that 1, you would get equals Y1. So you would get Y1 equals M times X1 plus B, which is our equation right here, except you're substituting in X1 for X and Y1 for Y, and then you would go down and do that for however many values of X and Y you wanted to have. So in this case, our X matrix is a 5 by 2, and our unknown matrix, B, it would be a 2 by 1, results in our 5 by 1 matrix for Y. So the first thing we want to do in linear regression through matrix manipulation is transpose the X matrix and multiply it by the transpose. So we're multiplying both sides of this equation up here. This equation right here is now being, step 1 is to multiply that by the transpose of matrix X. So now we have the transpose of matrix X, which is a 2 by 5 times a 5 by 2 results in a 2 by 2. So that 2 by 2 matrix is then going to be multiplied by our unknown matrix B, but we want to eventually, our goal is to isolate this unknown matrix B. So the first thing, like I said, we want to do is transpose X and multiply it by both sides. So now we have the transpose, and remember that the order at which you multiply matrices does matter, so we want the transpose out in front, because if we multiplied it the other way, say X times the transpose of X, we'd get a 5 by 5 matrix instead of a 2 by 2. So we want to multiply the transpose first times the X matrix, and then we're going to do the same thing on the right side. The first multiply the transpose of X times the Y matrix. So moving down, that was the first step, and then we combine them here. So like I said, this becomes a 2 by 2. This would become a 2 by 1, and B is still staying there because in this case it's our unknown, and that's what we're looking for. So after the first step, it becomes X transpose X is a 2 by 2 times B matrix times X transpose Y. So the third step would then be to isolate matrix B, because that's our unknown. So we want to take the inverse of the X transpose X matrix and multiply it to both sides. So when we do that in step 3, we have X transpose X inverse times the X transpose X, and then we do that to both sides. These will cancel out, and we're left with the matrix B, which is our unknown matrix, is equal to the X transpose X inverse matrix times X transpose Y matrix. And in relation to this equation, this would be our relationship is Sherwood number times some coefficient A, Reynolds number raised to the B, Schmidt number raised to the C. I'm sure you're aware of this now. And then we want to take the natural log first, both sides, so that we can get the powers down in front. So we take the natural log of both sides, we get the natural log of the Sherwood number is equal to natural log of A plus B, natural log of the Reynolds number, plus C, natural log of the Schmidt number. So when we're creating our matrix, we're going to have to column stack ones for A and the natural log of the Reynolds number in the second column and the natural log of the Schmidt number in the third column, and that is going to be equal to the natural log of our Sherwood numbers. And one thing to keep in mind is that this is ln of A, so when we get our final answer, the first, this will be our unknowns, so in this case our B up here will be this equation. So like I said, the one thing we need to remember is that this will return 3 values. We'll just call them X, Y, and Z. This first number X for A will actually be the natural log of A, so it won't actually be this this number. It won't be a, it'll be the natural log of a. So we will have to exponentiate that first element of that equation. But other than that, this is what matrix manipulation and linear regression looks like. And then we're going to head back to Python, and now we're going to create these matrices and then code that out and find out our A, B, and C using the linear regression model. So now that we have our we have a better understanding of what linear algebra is using matrix manipulations, we're going to create that matrix that we saw on in the last little bit ago. We're going to create that matrix using column stacks of 1, natural log of Reynolds number, natural log of Schmidt number, and then we're going to use that equation for finding the matrix of unknowns. In this case, it would be the coefficients A, B, and C. So we're going to start by defining, I'm going to keep the same variables as I used in the paper. X is our matrix, so we're going to use X as the, and then we're going to start with NP column stack, and we're going to start by saying we need ones. We need the column stack of ones to create that first column in the array. So we're going to use NP ones like. NP ones like, so that creates a stack of ones based on the dimensions of a certain variable, and we want to keep it to the same dimensions as the Sherwood number. So we're going to say NP ones like Sherwood number. So that creates a stack of ones based on the dimensions of the Sherwood number. And then we also want to create stacks of NP, the natural log, so that NP log takes the natural log, and then we want the Reynolds number followed by the Schmidt number. So NP log of the Schmidt number as well. So let's go ahead and, okay, so this is what it looks like. So this is possible values of the Sherwood, Schmidt, and Reynolds numbers. So we have ones followed by the Reynolds number, and then our natural log of the Reynolds number, natural log of the Schmidt number. So now, oops, get rid of that. So now we need to create our unknown matrix. So I'm going to keep that as B because I used B in the last one. And we want to use that same, let's go back real quick. We're going to use this equation right here, or B, our unknown, is equal to the transpose of X times X inverse equation times X transpose Y, which would be our, remember Y in this case is our natural log of our Sherwood number. So let's go ahead and go back to Collab real quick. And we're going to take the inverse of the transpose function. Now, taking the inverse is using the linear algebra catalog in NumPy, so we need to go back into our linear algebra catalog, which is the same catalog we use to find the rank of our matrix. And we need to say linear algebra, and we're taking the inverse. Remember, that is the inverse. Linear algebra.inverse, and we need to do that of x dot t. Using the dot t means it's the transpose of the X matrix, and then using matrix multiplication, you need to use @ sign. So we need to take the transpose times X, and then that is the inverse, so that's to the negative first, and then we need to multiply that. So again, matrix multiplication calls for @ signs, and then we're going to multiply that by, again, the other, go back really quick once again, we're going to multiply that by this right here. Transpose of X times Y, which is the natural log of our Sherwood numbers. So if we go back, we need another X dot T for the transpose of X times, and then we're going to use the NP log again for natural log, and then we want the Sherwood number this time. Let's go ahead and add another bracket there. Okay, so that is our unknown equation now. So now we should be able to print B and see what happens. So this gives us an array of negative 3.69, 0.822, and 0.443. So if we look at these numbers, 0.822 is really close to 0.83, and 0.44 is basically right on the 0.44 we have in the first equation. The only number that doesn't match up is the first one. And that's because we have to remember that, like I said, in the matrix manipulation, we have to remember that this is actually the natural log of our A. So we want to exponentiate that A. So the first element, we have to put that, we want to do we want to exponentiate, so let's say exponentiate the first element of that B matrix. Oops. And that gets us 0.24, which is extremely close to 0.23, so that makes sense. Let's go ahead and print B as well. So like I said, this isn't close because when I was talking about matrix manipulation, this was the natural log of A, and this is actually A. So now we have our A, B, and C using our linear regression method and matrix manipulation. So now we're going to talk about the other method, which is the sum of least squares. So now we're moving on to the sum of least squared method. And the sum of least squares method is, if we think about it, sum of least squares is essentially taking, let's say there's a line of fit and there's dots below it and above it. It's taking the distance between the data point to the line of fit, and it's trying to minimize or optimize the distance between each dot and the line so that the sum of least squares is the least. So we need to import a new function. So if we're going to try to optimize or minimize, which is an optimization problem, we need to, from our SciPy catalog, from scipy.optimize catalog, we need to import minimize function. So the minimize function will allow shift enter, will allow us to minimize the distance between our data points and our actual line of fit. So that is the best fit line for that, and that will return the coefficients of the best line of fit for our data. So now we need to check out the minimize function. So the minimize function takes a function within it and x0, which is initial guesses. So I guess the only way here is to, let's create a function then. So let's define a new function. We'll say the sum squares, and we'll say, I don't know, x, just actually not do x, we're gonna use x. Let's go A. So now we need to return a value. We need to return the sum of the, so we're going to use the empty sum. We need to return the sum of the differences between the Sherwood fit and our data points. So the difference between the Sherwood number, which is, again, it'll be that equation, and then we want to subtract from the line of best fit, we want to subtract the actual data points, which would be, in this case I used A, so the first element of A, which would be the coefficient A, so A times the Reynolds number raised to the second element of A, which would be 1. Remember that Python starts indexing at 1, times the Schmidt number raised to the second or third element, but A2. So now that we have the difference between, we have essentially the distance, so the Sherwood number is the line of best fit, and then we're subtracting from that the distance to the actual data point. So now we need to, if we think about that, if the data point is below, the distance will be negative, and if it's above, the distance will be positive. So we can do one of the two things. We can take the absolute value of that difference, or we can square the difference, so this is the sum of least squares, so I guess you can tell that we're going to square it. So if we square that number, it's always going to be positive, so that our error keeps growing and growing, and the negative value will not cancel out and make our graph look better than it actually is. So now that we're returning the sum of the differences, or the sum of least squares, we want to minimize or optimize that number. So again, we created a function for minimize, and that function was called sum squares. And the second argument is an array of our initial guesses. So our initial guesses, we're just going to use the 0.023, 0.83, and 0.44 that we got from our initial equation. So if we minimize, shift enter with that, we should get an array of values that are semi-close. So this array tells us that A in this case would be 0.26, B would be 0.81, and C would be 0.433. So those are all really close to these initial A, B, and C coefficients. So that looks like a pretty good fit, and we're going to go ahead and move on to graphing these data points.